These are the hardest problems, right? I call these transitor, okay? We're going to have translational equilibrium, and we're going to have rotational equilibrium, okay? So what we're saying is if something is, typically it's like something like this, right? We've got a cable or something like that, and then we've got a mass, okay? This thing, what we will say is this beam right here is not accelerating in the x direction, it's not accelerating in the y direction, and it is also not accelerating in a rotational way, okay? So what we do is we just say all the sum of the forces in the x direction is 0, the sum of the forces in the y direction is 0, and the sum of the torques about any point we choose to pick, right? And there's a little bit of strategy there, okay? All of the torques will add to 0. It's not accelerating. If it's not accelerating, it's a bit like green eggs and ham, right? Okay, you don't like green eggs and ham, and I don't like them in a car. I don't like them in a jar. All that stuff, right? It's not accelerating in the x, not accelerating in the y, not accelerating in rotation. It's not accelerating at all. Sam, I am. Yeah, that joke generally doesn't work so well in class. Apparently, people don't read green eggs and ham. But anyway, that's what we're going to do. So we're going to set up expressions. Now, typically in these problems, this is a pretty simple expression. Okay, the force in the y direction is fairly meaty, because we'll have the force of gravity acting on the beam in 2 places down, and then there'll be a component of this acting up, and then the wall might act up or down or something like that, right? So the y direction is fairly exciting, and then the torques are just that's where it all happens, right? Okay, so what I always do is I just always set up x, I set up y, right? And then I set up the torque expression. Usually we start with this. Almost always you can solve the torque expression if you set it up cleverly, and then you can plug that into the y, and then you can plug it into the x. Okay, it doesn't matter what order that goes. Okay, and so these are the steps I do. I always draw a picture, but I'll give you a picture, right? This is the key, though. You're going to want to do this. Draw arrows for the forces, and also make a note about where the force acts. Does it act at the left side? Does it act 2 meters from the left side? Does it act all the way on the right side? Okay, how far is it from a point? And I'll give you this clue too, is that we almost always pivot about the left side, just where the wall attaches. Okay, but anyway, just make a note of where the thing is actually acting on this beam, right? Calculate the weights, and what I tend to do is, let's say the beam is 12 kilograms. I tend to write the weight as 12g, where g is, we just assume that g is 9.81 newtons per kilogram. Okay, so when you see me writing 12g, that's what I mean, is that g is I'm multiplying by g. I just don't want to write it out because it gets to be kind of messy. My formulas look better when I do that, right? And then when I say express and calculate components, keep in mind that this the tension in this thing, right, has an x component that is to the left, and it's got a y component that's up, right? So this is theta, this is t cos theta, and then this side here is t sine theta, right? Those are the two sides. So when we say express the components, that's what we're talking about. And we've been doing this all along, so it should look familiar. Okay, so I think there's really very little for me to do, but to just show you there's 2 types of these problems that we do. One has an x equation, and then one doesn't even have an x equation. Okay, both types of problems have a y and a torque expression. Okay, so let's do I'm going to show you the type that has only these 2 formulas, and then we'll do one that has them all. Okay.